Let's look at a couple examples of word problems that are going to involve solving systems of equations. Here, two planes depart from LA International Airport and fly in opposite directions. The second plane leaves 30 minutes after the first plane, but its speed is 80 kilometers per hour faster than the first plane. Find the airspeed of each plane if 2 hours after the first plane departs, the planes are 3,200 kilometers apart. All right, so a lot going on here, and it looks a little bit complicated. Well, with all your word problems, when in doubt, as I always say, draw it out. Begin by drawing a picture. So we have these two airplanes flying in opposite directions. We've got plane one over here flying to the left, plane two over here flying to the right, and they are departing from LAX. Now, 2 hours after the first plane departs, the planes are 3,200 kilometers away from each other. All right, so we know that this total distance is 3,200 kilometers. What are we trying to find? Well, the problem says find the airspeed of each plane. That's the airspeed of plane 1 and the airspeed of plane 2. Notice that there are two unknowns. And whenever you have an unknown value in a word problem, it's always a good idea to assign it a variable. I have decided the airspeed of plane 1, we're going to call that V1, and the airspeed of plane 2, well, let's call that V2. Here we have two variables. Hopefully you're beginning to think about systems. We've talked about it. If we have two unknowns, that's going to require us to come up with two equations in order to solve the system. Well, let's think about coming up with some equations. We are dealing with speeds, we are dealing with times, and we are dealing with distances. Is there a relationship between distance, speed, and time? Hopefully you guys know distance is equal to rate times time. Okay, the distance that an object travels is equal to the rate at which it travels times the time that it has been traveling for. And in this case, we know that the total distance between airplanes has to be 3,200 kilometers. That's the distance that plane 1 has traveled to the left plus the distance that plane 2 has traveled to the right. Well, let's think about the distance of plane 1. The rate of plane 1 is V1, and it has been in the air for 2 hours, right? 2 hours after the first plane departs. So this distance here is going to be V1 times 2 hours. V1 times 2 hours. This distance that our second plane has traveled is going to be V2, that's the airspeed of plane 2, times, well, how long has this one been in the air? A half hour less, right? The second plane leaves 30 minutes after the first plane, so that's going to be V2 times 1.5 hours. Now, when we add these two values together, they have to give us 3,200. 3,200 is equal to V1 times 2 hours plus V2 times 1.5 hours. There is our first equation. Again, we have two unknowns. That means we're going to have to come up with another relationship between our variables. Let's take a look at the second sentence here. The second plane leaves 30 minutes after the first plane, but its speed is 80 kilometers per hour faster than the first plane. That means V2, the speed of the second airplane, is going to be equal to V1 plus 80. It is 80 kilometers per hour faster than the first plane. So, what did we just do? We came up with another relationship between our variables and generated a system of two equations and two unknowns. So to solve this system, well, our best method here is going to be substitution. The nice part is that we already have V2 isolated. So we can take this quantity V1 plus 80 and substitute it into the top equation. This gives us 3,200 is equal to 2V1 plus the quantity V1 plus 80 times 1.5. Continuing with our algebra, we can distribute the 1.5 through. This gives us 3,200 is equal to 2V1 plus 1.5 V1 plus 120. Combining like terms, 2V1 plus 1.5 V1, that gives us 3.5 V1. and subtracting 120 from each side of the equation gives us 3080 is equal to 3.5 V1. And to solve for V1, we can divide both sides of the equation by 3.5. This leaves us with V1 is equal to 880 kilometers per hour. Now that we know what V1 is equal to, we can back substitute this into our second equation of our system to determine V2. V2 is equal to 880 plus 80. That gives us 960 kilometers per hour. That is the airspeed of the second airplane. All right, so if you are solving a word problem, if you have an unknown, give it a variable. In this case, the two unknowns that we were trying to solve for were V1 and V2, the airspeed of each plane. And recognize if you have two unknowns, that's going to require you to come up with two equations that relate your variables. Let's look at another one here. A little econ example. The demand and supply equations for a new toy drone are shown below, where P is the price in dollars and X represents the number of units. Find the equilibrium point for this market, the market for this drone. So the equilibrium point is the price P and the number of units X that satisfy both the demand and supply equations. In other words, all we're really trying to find is an ordered pair X comma P that satisfies both of these equations. That means we are solving the system that includes our demand and supply equations. Well, graphically speaking, if we were to plot both our demand and our supply equations, we would end up with two lines. And as you guys know by now, the solution to a system of equations is going to be their intersection point. This point right here, that is going to be our equilibrium point. Okay, again, the price P and the number of units X that satisfy both equations. So how are we going to solve this system of equations? Well, the nice part is both of these equations are equal to P. And so all we really have to do here is set these two equations equal to each other, right? We are essentially substituting in this entire quantity for P, right? Setting the two equations equal to each other, we get 150 minus 0.00001x is equal to 60 plus 0.00002x. We can combine like terms, adding this entire quantity to both sides and subtracting 60 from both sides of the equation. That leaves us with 90 is equal to 0.00003x. And then we can divide both sides of the equation by 0.00003, giving us x is equal to 3 million units. All right, so that is the optimum number of units for this market. To find the price, we can now back substitute this quantity into either one of these original equations. I chose to plug it into the second equation. P, the price, is equal to 60 plus 0.00002 times 3 million. Plugging that into your calculator gives us a price. P is equal to $120, right? And so that is the equilibrium point for this particular market. 3 million units at $120. That is the optimum number of units and price for our toy drone. Okay, so there you have it, a couple word problem examples that involve solving systems of equations.